Well, hello again. I've got a short and I believe straightforward video for you today. I'm going to talk about thermal expansion of materials. So what happens when you heat up something or when you cool it? So suppose I have an object like a rod of iron or copper or something has an initial length L naught, and I heat it somehow. So most materials, when you heat them, they expand. So its length will change. It will grow by some delta L. Now it won't always come out one end. It uniformly grows, but I'm just drawing it as if it comes out one end. That delta L, that increase in length, is pretty easy to understand. It depends on how long it was to begin with. Longer material, longer objects expand more. So it depends on that L naught. Depends on how much the temperature changes. So delta T, the change in temperature. And it depends on what material it is. So there's an alpha here, something called the coefficient of linear expansion. Coefficient of linear expansion. Because different materials expand different amounts. Aluminum may expand a lot, steel may be less. There's a material called Invar that expands very little. So different materials expand different amounts. So that's where the material dependence comes in. So, for example, alpha of steel, well, there's different alphas for different types of steel, but an approximate value is 12 times 10 to the minus 6 degrees Celsius to the minus 1. So reciprocal degrees Celsius. So let's do a quick example. Suppose I have a rod of steel and I have a ring of steel that I want to put over that rod. And this rod has a diameter of 1.002 centimeters. And the inner diameter of this ring is 1.00 centimeters. And sometimes people do this so you get a permanent connection. If I can heat this up and expand it, by the way, if you heat it up and expand it, the hole gets bigger, not smaller, because the molecules out in here are getting further and further apart as you heat it, and that makes the hole bigger, not smaller. Anyway, so if I heat this up, I can heat it up and drop it over this object and get, something like this, and then they're permanently attached. You can never get them apart again. So it's a way of attaching two objects without having to weld them. So what I want to do is heat this enough to put it over that. So what I need, therefore, is a delta L of 0.002 centimeters. That will make it just fit. I really need to heat it more than that. So this will tell me the minimum temperature for it just to fit. Then I'd have to heat it more. So using this equation, my temperature difference will be delta L over alpha L. Since I'm going to have a delta L over an L, I can use them both in centimeters, and the centimeters will cancel. So delta L is 0.002 centimeters. Alpha is this 12 times 10 to the minus 6 degrees Celsius to the minus 1. L naught was 1 centimeter. And when you do all that, you get 167 degrees Celsius. So maybe I'd want to heat it to double that temperature to give me the extra space to just slip it over it, and then they would stay together as if they were just one object after that. So this is called linear expansion. We can also have area expansion. If I start with some object with some initial area A and heat it, it will grow by some delta A, and you get basically the same sort of thing. Delta A is some gamma A naught delta T. This is the coefficient of area expansion. And it turns out gamma is approximately 2 alpha. for most materials. Not alpha squared, but 2 alpha. If I have some volume V naught, you can have volume expansion. So if you heat it, it will get bigger as well. So there'll be some delta V, will be some, let's see, I think beta is what's used for that. Yeah, beta V naught delta T. This is the coefficient of volume expansion, beta. Turns out beta is approximately 3 alpha. Now these are approximations. You can also just look up gamma in a table, look up beta in a table, and use more precise values. All right, so that's expansion. That's linear, that's thermal expansion. Also works the other way. I could, for example, have cooled this object and had slipped it into the hole there. And the equation would have worked just as well that way. So that's really all for today, and we'll practice that in class. See you soon.